Hello, everyone, and welcome to the Design++ seminar series in the fall semester 2024. So the seminar series is normally organized by the Design++ team. It is based on Design++, which is the Center for Augmented Design and Architecture and Engineering and Construction. Yeah, thank you. Just needed the next slide. So we have we normally plan different talks throughout the semester. On October the 31st, there was already the first talk by Chris Solarski on game design. And if you would like to rewatch it, we have also a YouTube channel where you can, as I said, rewatch all the previous talks from before and also the talk from the last time. One thing that I maybe forgot to mention, that the seminar series was mainly organized in the background by Design++ with the goal of knowledge transfer. And in the beginning, it was purely an event. From this semester on, it also became a lecture for PhD students, which is quite a nice thing. And yeah, enough, I would say, from my side. In this case, I would like to introduce you our today's speaker, Olga, Prof.Dr. Olga Fink. She is an assistant professor of intelligent maintenance and operation systems at EPFL since March 2022. Her research focuses on hybrid algorithms combining physics-based models and deep learning, operational digital twins, transfer learning, and reinforcement learning for complex infrastructure maintenance. Previously, she was an assistant professor here at the ETH from 2018 to 2022. And additionally, she is an editorial board member of several prestigious journals, like the Mechanical Systems and Signal Processing or Engineering Applications of Artificial Intelligence. She was honored in 2018 as one of the top 100 women in business Switzerland. She earned the distinction of being recognized as a young scientist of the World Economic Forum and was honored as a young scientist of the World Laureate Forum. And in 2023, she was distinguished as a fellow by the Prognostic and Health Management Society. So the topic of today's talk is leveraging inductive bias for physically consistent machine learning applications in engineered systems. This talk will explore various forms of inductive bias applied in engineered systems with a particular focus on heterogeneous temporal physics-informed and algorithm-informed graph neural networks with applications in virtual sensing, modeling multi-body dynamical systems, and anomaly detection. Yeah, with this said, Olga, thank you for being here. Thank you for taking your time. And the stage is yours.
Thank you very much. Thank you very much for the invitation. Thank you very much to all of you for coming. It's nice to be back. I haven't been actually in that, I must admit, I haven't been in that building for the entire time that I was at ETH. It's actually a shame, so it's the first time that I'm in that building. But it's actually nice to see it. I always saw the pictures and the videos. So thank you very much for showing up and showing interest in the topic. Just to know what background you have, so who of you would consider themselves as machine learning enthusiasts? Not that many. Okay, what other topics? Architecture, civil engineering. Anything that I did not cover? But actually, the talk is really focusing on algorithms, so please bear with me, and I hope you will be able to appreciate the algorithms while I'm exposing you to that topic. So maybe before we start, I wanted to introduce which topics we are, or which type of problems we are normally aiming to solve. So if we consider the travel wheel, And kind of on the example of the railway wheel, what we are aiming to do is, on the one hand, to detect a fault, so to be able to tell if there is a flat or shelling or non-roundness or any type of fault. But then what we are aiming to do is to be able to distinguish between different fault types. So to be able to tell if it's a shelling or if it is a crack that is appearing. But ultimately what we aim to do is not just to do that, but really to monitor the evolution over time and then to be able to predict when it reaches a critical level. And for the case for non-roundness, this would be possible so that we are able to monitor it over time and then really tell when it reaches a critical level. So these are typically the three tasks that we are aiming to do. And it depends how much data we have access to, but typically we focus on data-driven algorithms. But if we consider data-driven algorithms, and particularly machine learning algorithms for engineered systems, and because we're in the setup of rare events, because faults are actually not happening that often, we have a couple of challenges that we need to deal with. And we need to solve these challenges in order to be able to solve the problems as well. So on the one hand, we have this challenge of limited data availability, because on the one hand, either we are not monitoring the system properly or kind of all the time, but also we don't have sufficient faulty samples that we would be able to learn from. And we typically have quite diverse operating conditions that are appearing, and this is what makes it challenging for a machine learning model to learn from. But what we typically require as well, because those are very long-living assets, we do require very long prediction horizons. And because of that, and typically machine learning algorithms are not so good in very long prediction horizons, we need to deal with the accumulating error as well. And because we deal with safety-critical systems, what we would require is not just to tell that something will fail, for example, but really to be able to explain and to provide evidence as well how the system condition will be evolving. So this is why we need interpretability. And one of the challenges or general challenges of machine learning is that they're typically not so good in generalizing very well. But what they are not at all not good in is in extrapolating. So if you learned it on a specific system with a specific geometries and designs, if you want to apply it to a system that's larger, for example, or needs experiences larger loads, the machine learning algorithms will fail in such setups. So this is really what they're not so good in. But typically, we do require that those systems would need to extrapolate as well, because this is what we are experiencing in real-world situations. And in order to tackle those challenges, kind of the way, or part of the way that we have been tackling is on the one hand, using as much information as possible from what we already know about the problem and about the underlying physics as well. So it's really integrating the prior knowledge and the physics into the deep learning models. And there's been actually quite a lively research field. So there has been quite a lot of research going on. And in fact, physics-informed machine learning has been even put as one of the hype topics on the Gartner's hype cycle for AI. So it means, so it went from a niche research field into something that's getting a bit hyped as well. But the question is, how do we actually integrate that physical information or the prior information into the models? And in fact, there are three different ways on how to do it. So on the one hand, we can have the observational bias when we, for example, produce additional samples from simulation models, then adapt them. So this is kind of what we would consider there. If we then consider the learning bias, so those of you who are familiar with the physics-informed neural networks that were introduced or co-introduced by George Kaniadakis, this is where we integrate an additional loss in the training function, and when we kind of force the algorithms to follow the underlying physical equations. So that would be the learning bias. And then what I wanted to focus with you today is on the inductive bias. And that's kind of one of the stronger forms of introducing that into the learning architectures and the algorithms. So what is inductive bias? It's kind of all the assumptions that we know about the problem that we integrated into the learning algorithms. And just to give you kind of 2 examples, and then it becomes probably much more visibly understandable. So for example, in linear regression, we're actually assuming that the relationships between the input and the output are linear. And this is a strong assumption, and this is what we're actually integrating into that model when we are solving it. But another one is and actually quite a popular one, is the one on the convolutional neural networks, where we have the assumption of using kind of the local information about the neighboring pixels and extracting the patterns and are really applying them in different regions of the image. And then aggregate them as well. So we assume those spatial hierarchies and also the location invariance of some of the patterns that we are learning. So it's something that we know about the problem, and then we integrate it into the algorithm and make it by then obviously better solvable. But then if the assumptions don't hold, obviously the algorithm is also not that usable as well. And what I wanted to show to you today is a couple of examples on how we were aiming, or what type of algorithms we were developing, and what type of information we were actually integrating. And the first work that I wanted to share with you was actually one of the last works that we did here at ETH, and it got really published kind of, just at the time when I was leaving. And the idea here is to integrate or to use the prior information from signal processing and integrate it into the learning architectures of machine learning algorithms. So since not many of you are kind of signal processing enthusiasts, I still have the architecture that is kind of underlying it. So probably you're not that familiar with the signal processing architecture, but in fact it's the same architecture that the sparse way the wavelet networks would be using. And what we actually did here is that we substituted the signal processing blocks by the learning blocks by the proposed denoising sparse wavelet network. So basically, we used the very same architecture that is very commonly used in signal processing, and then we just substituted the processing blocks with the learning architecture here. In fact, it was a work that was led by Dr. Gabriel Michaud and Dr. Gaetan Frisk as well. And one of the requirements that we needed here as well is to introduce a thresholding function, because this is what we require in order to decide which of the wavelet bands we actually need to focus on. And this is the hard thresholding function that we proposed in order to learn kind of on which part of the signals it should really focus on. And this really worked actually quite well in different setups where we don't require additional hyperparameter setting, is similarly performed here for the fast discrete wavelet transform, but now it's kind of becomes really learnable. And we applied it to one of the setups of detecting anomalous sounds, the anomalous sounds in different types of machines, such as valve, fan, pump, and slide rail. And the task there was to recognize an anomalous sound without knowing how an anomalous sound actually sounds like. So just from knowing how a normal sounds like was the task to be able to distinguish between the two. And in fact, so this was the performance that we achieved, and it was outperforming the baseline quite significantly. And the baseline was the signal processing with on top and machine learning algorithm on it. And this is kind of one of the principles. How do we benefit from something that's already well interpreted and well understood by the domain expert, but then integrate the learning element into it, and then improve the performance there as well. And one of the other directions that we have been following quite a lot, actually, and particularly since I left ETH, it was really one of the new directions that we started, is making use of the spatial connectivity, but also the similarity between the time series, but also between the sensor measurements. And this is where we really started working on graph neural networks. So if you consider where we actually encounter graphs, and it's really like in many different applications, many different locations, such as if we consider the spring mass system. But even if we consider the motion dynamics, we can represent it as a graph as well. Molecular dynamics, but also particle dynamics. So it's quite a lot of different systems that can be actually represented as graphs, and where we can consider it as pairwise interactions and learn the pairwise interactions. And this is where we do incorporate, or one of the ways is incorporate the spatial inductive bias, where we do take the information on how the systems may be physically connected. And there's actually two directions, and I will show you both of them. But in fact, if we consider kind of engineered systems as well, we would encounter graphs there as well. So for example, this is in a district water distribution network. We could represent the sensor locations of the pressure as a graph. But interestingly, we could also consider a bearing and the dynamic model of the bearing as a graph as well, where we actually represent the inner ring as a node, the outer ring as a node, and then the roller elements as nodes as well, and then connect them and learn the pairwise interactions and the pairwise dynamics. So we can represent quite a lot of systems as graphs, but the question is, do we need something else, or can we just rely on that graph connectivity? Because otherwise it would not be also that novel as well. But one of the challenges that we encounter as well is that whenever we consider those sensors, the sensors are actually measuring different quantities, but also different types of quantities. So for example, if we consider an accelerometer measurement, an accelerometer sensor, and the strain sensors, on the one hand, one is actually measuring quite high frequency signals, and the other one is rather measuring kind of slowly evolving dynamics. So if we combine all of the sensors, it actually may not work that well at the end. And this is where we started working on this heterogeneous temporal graph neural networks to enable the learning architectures to learn in different ways from different types of sensors, but still learning the interdependencies between the sensors. And this was actually this is the architecture that we proposed for this case. What we actually do is, on the one hand, we are handling the low frequency signals in a different way and processing them in a different way compared to the high frequency sensors. We then still combine them, and we learn the heterogeneous interactions. On the one hand, the interactions within the same modality, each of them independently, but then the interactions between the different modalities, and then we combine them, and then we solve the task, whatever the task is that we aim to solve. And this work was led by Mengji Zhao, who is a PhD student in my group. Actually, the case study on which we developed it was a case study of a virtual sensor of a big bearing that are typically applied in wind turbines. And what we would be interested here is to be able to estimate the load based on the measurements of the operation. So this was a test rig on which it was actually measured, and we have access to vibration measurements, but then also to the temperature measurements, because obviously temperature, the higher the load, the higher the influence on the temperature. So it is important to integrate both of them, not just to focus on the vibration sensors, which are actually capturing the changes particularly very fast. So this was then the different types of graphs that we developed. So the blue ones would be the temperature sensors. So, there were in total 9 temperature sensors located at the entire circumference. On the one hand, we connected each of them, but then we also connected those that are opposite to each other. We did not have that many vibration sensors, but then we also created an independent graph for them. And then we also had the heterogeneous interactions in the one, but also in the other direction as well. And because there were kind of two bearings mounted on the same test rig, we also had the interaction between the two. So just to show you how it actually worked, we compared it to quite a lot of different architectures. The one at the bottom is the one that we have, that we proposed. What we saw was actually that the performance improved for different, kind of under all the different rotational speeds quite a lot, and was really kind of performing much better compared to the baseline models, because really it was able to use the information from both modalities and to learn the particular interactions between them. So what is the inductive bias that we integrate here? The inductive bias in this is the information on the heterogeneity of the sensors, but also how they are interacting with each other, and how to integrate that into the learning architecture and to process them. And as the next way of introducing inductive bias, what I wanted to discuss with you is how we can actually make use of the classical algorithm and then integrate them into neural algorithmic reasoning. So what are classical algorithms? And kind of just to have some examples would be, for example, the Bellman-Ford algorithm, which finds the shortest path, or the majorization, minimization algorithms, which converges to stationary point. Just kind of some of the examples to tell. But what they have all in common is that they are provably correct, they are generalizable, and obviously they are interpretable. So whenever we find the shortest path, obviously we will be able to follow it as well. But one of the challenges that they face is when we want to apply them to real systems, this is where it's kind of difficult to transfer how to model then it in the real system and really to get all of the specificities to it. So for example, if we want to use it for natural inputs, is much more difficult to implement it in such setups. And kind of a couple of years ago, a group in DeepMind introduced this new architecture on algorithmic reasoning. And the idea there is to generate synthetic data that would be, and then train the algorithm to really solve or kind of replicate the results of the algorithms. And once this is trained, we can actually use this processor, and what we would just substitute is this encoder and the decoder, and then fine-tune as well. And this would enable us to benefit from this algorithmic reasoning part that we actually trained on the classical algorithm, but then we can now make use of it and then still benefit from their unnatural inputs and really to solve the real problems as well. So in fact, I think it's part of Google search as well, so Google Map search. So this was part of what they integrated in Google Maps as well. So it's kind of a very neat idea that we can make use and integrate the knowledge from classic algorithms, but then still apply them to natural problems and natural inputs as well. And this is where we actually started looking into it for the problem of leakage detection. And this was work that was led by Zepeng Zhang, who is a PhD student in my group as well. So on the one hand, we have the challenge that the sensors are actually quite distributed, but also that the sensors are rather sparse. So it's rather difficult, on the one hand, to detect leaks, but also to locate leaks as well. That's why we really need to estimate all the information on the entire graph, on the entire network, from the sparse measurements that we can obtain. And this is where we started looking into how we can benefit from graph information and then integrate it into the learning architecture. And the closest algorithm that we actually found that would be rather similar is the Ford-Focuser algorithm on the max flow estimation. So the idea would be that, what the algorithm actually solves it allocates what would be the additional maximum flow that would be possible on the network given the defined capacities. And it kind of aligns rather well to the problem that we had in mind. So then we trained the algorithm to solve this algorithm, and once we trained it, then we then took it, and then on the one hand we used it to reproduce or to reconstruct and to predict the observed pressure, and then we substituted the encoder and the decoder architecture, and then fine-tuned the model as well. And we had a dual task, on the one hand to reconstruct the current measurements, but on the other hand to predict from the past period, from the past observation, the current observations. Obviously, if they deviate, then there should be a leak that we may observe. But what we also wanted to evaluate is, can we actually use this additional information that we trained our algorithm, that we trained to solve this algorithmic reasoning in different ways. And the question is, can we actually, on the one hand, augment it as an input, so use it really as an additional input to the model that we had, but also to feed it into another location, so to feed it in at the last layer before and provide us an additional information to the embedding. So we evaluated the three different setups. On the one hand, kind of without anything. On the other hand, the classical setup. And then the two other setups where we introduced it as an additional input, and where we introduced it at the last layer as well. So it showed that it actually was working rather well. It was using this information effectively. But one of the challenges that we also, or one of the problems that we wanted to ask ourselves is, can we actually rearrange the location of the sensors and then still predict the same amounts? So would the algorithm be able to generalize when we change the locations? And this was actually the answer. So on the one hand, this was kind of the general, or the algorithm that was not using any additional input. This is the classic algorithmic reasoning algorithm, and this was the case when we used this part of the encoding architecture of the encoder as an additional input. And what we actually saw was that apparently it was able to generalize really well to cases where we really changed the sensing locations. I wanted to show you two more examples, and these are actually some of the examples that we are quite excited about. And what we are using here is, on the one hand, considering the physical connectivity, but also introducing some basic physical knowledge into the architecture. And reinterpreting really the message passing. So some time ago, Google DeepMind introduced the so-called graph neural simulators, and they were really working quite well for a lot of different simulated cases. That's kind of a bit the background, what we're doing. So we are using, we need to define the features of the nodes and of the edges, and then we encode them, we process them, and then we perform message passing, and then we decode them at the end. So that's kind of the basic setup. And this is how it looks if we train as a simple mass spring system, but we trained it on 4, 5, 6, 7, and 9, and 10 masses, but now we have actually 12. And what we see is that it really starts deviating immediately, or kind of quite soon. So obviously it was able to interpolate quite well, but not extrapolate to something that it hasn't seen before. But what we propose instead is actually to change this and to, on the one hand, impose on how we process the symmetry preservation. So really impose that the edges in both directions actually equal in opposite. But then also the question, how do we process the message passing, and how do we, that we reinterpret it as solving the Euler integration for the forward Newton dynamics. So basically we take a similar architecture, but now we impose additional information that we know about the system and what we know that should be actually preserved and how it should be computed. And then we adapt this kind of how do we encode the information, but also how do we process it as well. And these are the new features that we introduced in this case. And this is the same what you saw before. And this is now the architecture that we actually, or based on the architecture that we propose. And as you see is that it's actually able to follow it for really quite some time and kind of extrapolate also to cases that it hasn't seen before. So apparently this is quite a nice property that we do require in many setups. And this is when we applied it to a bearing case where the task was also to estimate the load without having seen or without having any supervision, but just by observing how the rolling elements are actually moving in time, it was really able to quite accurately infer the properties, the physical properties, without having any supervision at any point in time. And the last case study that I wanted to share with you, again, deals with an inductive bias, and the inductive bias focuses now on making use of the topology itself, but again, making use of kind of integrating additional physical information on how the messages should be processed, but also how the objects move actually, and to which laws should they follow. So if you consider kind of a standard mesh, this is how we would represent it. And if, at least in the case of graphs and meshes, when we process them, so, usually there is no hierarchy attached to it. So we have the typical nodes and the edges. But what we propose here is, on the one hand, that we still consider the nodes and the edges, but we now also use the faces or the cells. And once they come into contact, we also have the interactive cells. And that we also have the entire object that we define as well. And then we can adjust the information that where we attach it and how do we learn it. And now it becomes also possible to exchange information at all the topological layers. And that's kind of the processing steps. On the one hand, we need to enhance the mesh faces and to propagate the information of the intra-object data to the specific nodes and faces. Then we process the inter-object collisions because we need, on the one hand, to detect if there is a collision happening or not and process this in a different way. Then we update the individual objects and nodes, and then we predict the accelerations at the next step. And as mentioned, we also add the additional information on how we actually compute those interactions and how do we update the positions also after the collision as well. So we compared it to the state-of-the-art algorithms, which is the mesh graph net and the Fink net, and the one on the right that you see is the algorithm that we propose. And it actually was compared on different degrees of difficulties for different objects. And this is just one example on how the objects are actually colliding. And when you start seeing kind of the deviation, so this is kind of the error that we see, so the ground truth is the opaque area here. So what we see is that after 100 steps, it starts deviating a bit, kind of deviating on quite difficult, on quite complex objects. And we also compared, is it the information really useful for us or not? Even though we are integrating this additional information, do we really benefit from it? And if we leave it out, do the algorithms perform in a similar way? So on the one hand, we evaluated, for example, that does this center mass distance that we encoded additionally as an object feature, does it improve the results? And in fact, it does improve the results. But also, if we integrate this additional physical information, how would it perform in this case as well? So it does show that when we integrate this additional inductive bias on the one hand on the topology, but also on how do we interpret the different properties and how do we process the interactions and the messages, it does improve the results quite significantly. So this was the slide that I actually started with, and what I was trying to show you is that there are actually different ways on how we can solve those challenges. And the way to solve it is to use the prior information and then adjust and develop the algorithms and the architectures further. And in fact, we did achieve quite some improvement in terms of the different challenges that we see here. And with that, I would like to end. It's just at the center of what we have been doing. I would like to thank our industrial project partners, the funding agencies, but obviously also to my amazing team who have been working on a lot of different topics. So thank you very much, and I'm happy to take any questions that you may have.
Yeah, thank you, Olga. I think you showed very nice examples, and I think we can all agree that we see that machine learning is going further, and we see that it's also coming in the structural design and those fields, like you showed it right now. And I think the next step is to recognize it, and we see the possibilities, but the next step is in the incorporation of the physics and boundary conditions to make it more understandable. So yeah, I think that was a very nice example. Also with the inverse idea of the exploration of the design space.
But isn't it not just improving the interpretability? Because we are generalizing much better, but also we are extrapolating. And partly we need much less data to train the algorithm and so on. So it's kind of tackling at different levels. So it does bring benefits at different, for different problems at the same time.
Interesting to explore the database. So is the data that you use purely synthetic, or is it also like recorded from actual systems, or how's the process to incorporate this data?
It depends on for the different case studies that I was showing. The cases were different. For example, for the bearing case study, this is where we collaborated with an industrial partner, and this is where the data was collected on the test rig. But part of the idea is really to get it from real applications as well, from field data as well. For the other examples that I was showing, it's mostly from models, because this is where we kind of need to have the real ground truth in order to be able to validate the model applicability. But we do have quite a lot of industrial projects, so we do have kind of real data. It's just when we need to show how the algorithms are working, we typically need to show it on something that we can trust and where we have the true ground truth.
That's the thing, always finding this true ground truth. It's also, I mean, the same in our field. We have to be very sure about the actual problem in order to be able to simulate it and take the simulated data actually for training. But yeah, that's challenging at some points, depending on the problem. But yes. That's always the struggle.
And it also depends on the quality of the data. And
exactly, yeah, like the scatter of the data and so on.
Yeah. Also on the project partner that we may have, because some are kind of more organized or more strict in terms of how they collect the data. So it depends a bit as well.
Follow up on some discussions at the Apero. Olga, thank you very much for being here. As I said, for taking your time and for the talk. I would like to introduce the next talk held by Prof.Dr. Mena El-Asadi. It is called Intelligence Augmentation, Bridging Human and Artificial Intelligence. And yeah, with this said, I would like to invite you to the Apero. And thank you once again.